This program was sponsored by the Jesse and John Dance Fund. Since 1962, these lectures have been a forum for distinguished scholars of national and international reputation who have concerned themselves with the impact of science and philosophy on man's perception of a rational universe.
My name is Marcia Landolt. I'm the Dean of the Graduate School. And on behalf of the Graduate School and the University of Washington, it's a real pleasure to welcome all of you to this evening's Dan's lecture. We're here tonight because of a very generous gift to the University of Washington. This visiting professorship program was created in 1961 with a bequest from the estate of Mr. John Dance. Mr. Dance came to Seattle in the early 1900s and became a very successful businessman. He is perhaps best known for the chain of movie theaters that he developed. John Dance was a self-educated man who read widely and liberally. He was fascinated by scientific developments and was particularly interested in the philosophy of humanism. In creating this endowment, his goal was to bring to the University of Washington and to the Seattle area distinguished men and women, and this is a quote, who have concerned themselves with the impact of science and philosophy on man's perception of a rational universe. Mr. Dan's wife, Jessie, shared the vision that he had and augmented the endowment with additional gifts until the time of her death. Please join me in expressing appreciation for this gift and to the members of the Dan's family who are with us this evening. Our speaker tonight is George Coyne, and he will be introduced to you by a professor in the Department of Astronomy, Dr. Bruce Ballack. Please welcome Dr. Ballack.
Welcome to you all. All the Dan's lecturers are invited to the campus as a result of a nomination process from departments. And in the case of George Coyne, we must have had a record number of departments that endorsed his nomination. Astronomy, obviously. History, Italian studies, philosophy, comparative religion. Again, we're all involved in the nomination process, and we have very strong endorsements from the president of Seattle University, the dean there. George is just a person who works in many different areas, is well known to all of us. But before I get any further, I want to also mention that there may be a special show tonight on the way out, thanks to a huge solar flare. How many people have heard about the flare? So, I have a movie here. Let's see if I can get it to work. This movie represents 4 full days of photographs taken from a satellite which is orbiting the sun. And I will try to point out, flares are taking place all the time. In fact, somewhere right in there is a flare from last Friday, which the electrons and protons from which turned this picture fuzzy right at the very end. But if I go back here, so those are the particles from the Friday flare arriving at the satellite and driving the detectors absolutely crazy. But just a little bit down here someplace, hello, is a huge flare which occurred at 3 o'clock in the morning Seattle time a day and a half ago. And the first of the electrons and particles, the protons from that, arrived here early last night. So it was a 19-hour journey, 93 million miles. When you do the math, that's 5 million miles per hour. And these particles have rammed into the top levels of the Earth's atmosphere, even though the sun is in the quiet part of its 11-year cycle. This was the 3rd largest flare ever seen. So when those particles reach the Earth's magnetic field, they dive down into the poles, both of the poles. And if it happens to be nighttime, you'll see the effect of those particles stripping the electrons off of the atoms in the upper layers of the Earth's atmosphere and giving rise to an aurora. So I checked just before coming here to see how the aurora is behaving, and we're well within the band. Well, we're well within the band, but we're sort of near the edge. You may need to get away from the city lights in order to see the aurora, or maybe not. My guess is that you will. So on the way home, if you live in the suburbs or someplace where it's dark, don't take your eyes off the road until you hit a red light, but then look up. It might get interesting. How many of you have heard about the asteroid impact that took out the dinosaurs? Well, almost everyone. So one day the dinosaurs were gone. For millions and millions of years, the dinosaurs ruled the surface of the earth. They ate all the food. They filled all the ecological niches. And one day an asteroid impact came down, splashed into the Caribbean off the coast of the Yucatan Peninsula. Material was ejected into the Earth's atmosphere to such a degree that the food chain collapsed and the dinosaurs disappeared on timescales of just a few years. Without that, we wouldn't be here. What was bad news for the dinosaurs was the way for us to find a beginning. We mammals were then shrews living underground. But once the dinosaurs disappeared and the Earth healed itself from the asteroid impact, mammalian life spread across the planet, and that's why you're here. Similarly, let me get this right, in the 17th century, Galileo, through his astronomical observations, overturned 2,000 years of knowledge in astronomy, and he did other experiments that overturned 2,000 years of belief in physics. Before Galileo, we thought the Earth was the center of the universe. Galileo, the people who came before him, such as Copernicus, the people who worked with him, such as Kepler, and the people who followed, such as Newton, did something which is really, really remarkable. They moved the center of the known universe from the Earth to the sun, right? NASA wouldn't even dream of trying something like that. This was truly a huge event, not only in physics and astronomy, but also in all of science, because Galileo introduced the modern version of science, which didn't really exist in any established form at that time. I should really say that he catalyzed modern science. Modern science is an enterprise which builds on the universe the way it is. You take the universe for what it is, you interpret that, and come up with laws that we now call laws of physics and other areas of science. But up until that time, the standard idea of science was to verify the truths that had been revealed to us. George, I hope I'm not giving your talk for you. Right. This was a fundamental change. Science had never been done this way before. And the change in science came abruptly. Galileo himself was an incredibly brash person with an ego that just wouldn't stop. It took that kind of pressure to bring these changes on in a society that wasn't prepared to accept them. This forcefulness was a key part of Galileo's effectiveness. The point here is that science as we know it began, but science as it had been known didn't, like the dinosaurs, disappear from the face of the earth. And so a huge struggle began for the ownership of knowledge. Science as we know it now, evidence-based science on the one hand, religion on the other, with its own way of exploring plumbing the world for, in this case, for knowledge and information. This all began as a fight because people were afraid. They were being defensive and protective. In a perfect world, we, the scientists, and the people who believe in the spiritual realm, well, scientists believe in the spiritual realm. I'm drawing too sharp a distinction here. But we should all be working together to find our way forward in a very complex world. And yet, there's a fight that has been going on for 4 centuries. And tonight, we're going to dive right into the middle of it. Now you get rid of me. it is my pleasure to introduce a person who has walked this tightrope between science and religion. George Coyne is a scientist. He's an astronomer. He's published in every major journal, very, very prolific. When I speak to him, I know that I'm speaking to someone whose patterns of thought are much like mine. On the other hand, George is a devout Jesuit. There is just never doubt for a moment his loyalty to his religion. And yet, in some coherent way, George manages to see how science and religion need not fight, but can act harmoniously together to move forward. George has been the director of the Vatican Observatory for 25 years. He arrived just days before Pope John Paul II became the Pope. So John Paul II is celebrating his 25th year as the Pope. George is celebrating his 25th year as the director of the Vatican Observatory. The Vatican Observatory has expanded and blossomed under George's leadership. It is my pleasure to introduce a real intellect, a wonderful human being. George, welcome to the University of Washington.
We're going to measure the applause after my talk also. Thank you all for coming out on this bitter cold evening in Seattle. It's all relative, you know. I just arrived a few days ago from Tucson, Arizona, so I did get my jog in, but I had to cover myself pretty well today. Thanks to Marcia and Bruce for the lovely introduction. I should say a few words immediately about the title of my talk, When the Sacred Cows of Science and Religion Meet. When I first used this title in Toronto, as a matter of fact, a slightly different topic than I'm on tonight, but related, obviously, because I was able to use the same title. A clever journalist, they're all clever, these journalists, did a feature story saying, Jesuit priest scientist herds the cows. So I had to tell that audience, as I'm telling you this evening, if you don't mind, the title of the talk refers to the content of the talk and not to the audience. So while you are allowed to boo, you may not moo. Let's get on to being a bit more serious. What I would really like to do as a scientist is to invite you on a little journey into the universe. That journey actually, though the universe may not have an end, that journey has an end in the sense of a target. We're looking towards something. And the target is precisely this title. Do science and religion have anything to say to one another? And so I will be a scientist for about 2/3 of the talk, and then I anticipated the end of the talk by putting on my Halloween outfit immediately, and talk to you at the end as a person who also has religious concerns. In order to do this, I think I will use a series of slides that will allow us to take this journey rather rapidly. As we take it, I would like you to think upon the following. I use the word sacred cows to refer to the scriptural story of Moses going up the mountain, and God appears to him out of the burning bush. Before he went up the mountain, the Jewish people of old asked Moses to find out God's name. That's a very significant thing, because in most societies, in our own, to know a person's name means to bring them a bit into your intimacy, into your world view of things, especially if we use first names of people. It means that we know them. We've brought them into our ken, into our intimacy. And the Jewish people wanted to do this. They wanted to bring God down into their image and likeness, make God, they wanted to have an idol for God. So Moses went up the mountain and he asked God what his name was. And God said, I am who I am. Scripture scholars tell us that that has two very different meanings. One is very positive. I am who I am. That is, being God, I will always love you. I will always be faithful to you, even though you will wander, you will sin, you will raise up idols, etc. Nonetheless, I will be faithful to you. But it has a very negative meaning also. It says, I am who I am, meaning I cannot give you a name. I'm not like Judy or Frank or rock or tree or fish or proton or universe or galaxy. I'm none of those things you name. You cannot name me. You cannot name me in the sense of bringing me into your possession, into your intimacy. Moses comes down the mountain and he finds the people doing exactly what he suspected they were up to when they asked him to find out God's name. They have a golden calf and they're dancing around it and singing hymns to it. It's their God. Their God is within their circle. Now, that temptation, to my mind, as a scientist and a religious believer, is a constant and daily temptation. Religious people, we pray to God so that he will do what I want God to do. Take the extremely difficult case, a mother who has a young child with leukemia. The typical reaction of a mother who has religious belief is that, God, why did you do this to me? Of all the children in the world, I suffer a child with leukemia. We have to sympathize with that response. Nonetheless, it's a failure, in a sense, to open ourselves to the mystery of God, accept all that we have in human life, all the experiences, and not try and bring God down into my individual experience and make God fit what I think God should be doing. That's a constant temptation to me. It's my temptation every day to try and reduce God to what I think God should be doing. The scientists, more the people who view scientists rather than scientists themselves, look upon scientists as people who know everything. And that the scientific method, the way of doing science, is the way to real, certain, and true knowledge. That's where we really get to know it all. Big Bang cosmologies, quarks, all of this, they may be strange words, but we're really understanding what's going on. And there's no other way to really do it. Literature and poetry, philosophy, theology, all these things are nice human pursuits, but they never approach coming to the truth like scientists do. That's idolatry. That's an idolatry of science. It's making science into what I call a scientism, as if science were the end of everything, the only way to come to true and certain knowledge. There's an interrelationship here. And many people hold that the beginning of modern atheism is founded precisely on this, that the birth of modern science with Galileo, Newton, Leibniz, Kepler, have whom you will in that period. They were all very religious persons. And they tried to establish the foundations for religious belief on the same rational basis as they established the law of gravity, eventually the expansion of the universe. That is on a very rational basis. And that will always fail. Any attempt to establish religious belief on a purely rational basis will always fail. And it was a temptation to religious believers to view God as a source of knowledge, a source of explanation, rather than, to my mind, as a religious believer, what God really namely a source of love, a very interpersonal relationship. So much for the preaching, okay? I would like now to take you on this journey through the universe, but ask you to reflect upon this interrelationship, because if what I say about the idolatry, the temptation to idolatry of both religion and science is really true, then unless both sides understand this, unless both sides really appreciate the temptation, then when they get together to talk, there's going to be a lot of mooing, but nothing significant will come out of the discourse, the dialogue. I would like to attempt this evening to have a dialogue, but I'd like to establish first the scientific background to that dialogue. Let's begin our journey into the universe. I begin with this picture of Stonehenge. It's a megalithic monument in the Salisbury Plain of Great Britain. It dates to about 5,000 years before Christ, so about several millennia before the patriarch Abraham, let's say, before the birth of the principal religions that we know of today in our world, 5,000 years before Christ. It is at one and the same time, well studied by archaeologists, a temple where they offered worship to their gods, and an astronomical observatory, because they offered worship to their gods by sacrifices on these horizontal stones, but in the vertical stones, this is a reconstruction, they aligned these stones that they could study very accurately. When will the sun rise at the beginning of spring? How high will it be in the sky? How low will it be in the sky with the various seasons? In order that they could know when the rainy season was going to come, when to plant their crops, when to reap. In other words, they were studying. This is a telescope. This is an astronomical observatory in which they studied as accurately as they could the positions and movements of the heavenly bodies, but not to understand the heavens, the universe, but to live better on the surface of the earth. That's a very different thing, obviously, than we do today. We study the heavens to understand the heavens. But nonetheless, it was simultaneously a temple, a church, a place of worship, and an astronomical observatory. And there are many such monuments that archaeologists have uncovered. Well, where were the gods to whom they were offering their sacrifices? Obviously in the sky. So the Orion Nebula, they linked up the brightest stars to make this design in the heavens, and that design said that their great hunter, one of their great heroes, their great gods, the hunter Orion, was up there in the sky. The bear he was hunting is over here, his little hunting dog is down there. So they had all of this. The heavens showed them their great heroes, their great gods. Unfortunately, they did not know. For them, it's unfortunate. For us, it's not so unfortunate that these stars in general have nothing to do with one another. This star here, I don't know this exactly, but I'll say it anyway, is maybe 2,000 times further from us than this star here. In other words, we see all heavenly objects, the nearest to the farthest, the moon out to the most distant galaxy we can see, as if they were all at the same distance. And the simple reason is the distance between our eyes is so small with respect to the distance to the nearest celestial object that we see all those objects on what astronomers call the plane of the sky. But in reality, when we measure carefully the distances, this star would be 2,000 times further away from us than this star here. This, by the way, this is very much an aside. This lays the scientific death to anything like astrology. I mean, the fact that I was born when the sun was in the house of Capricorn, there is no house of Capricorn. It doesn't exist. So any attempt to, do that kind of silly thing. If you do it to be silly, that's fine, to have fun, okay? But if you do it to be serious, you're in big trouble. However, in the universe, if we look today as scientists to this God in the heavens, what do we see? So look at the paunch of Orion, and this is what you see. A bunch of gas and dust. Notice that the blue is here and the red is here. We'll come back to that. But these incandescent regions, what is this? This is a stellar womb. This is where stars are being born. And when Hubble Space Telescope looks in detail at a little piece of that stellar womb, what does it see? It sees this. Oh, what a lovely picture. Look, it's red over here and it's blue over there. Let's blow it up a bit. And you may look at it and say, isn't that nice, this distribution of colors? A scientist says, why? What does that mean? Why is most of the red gas here and most of the blue gas there? There's a very simple reason. The first young, most energetic stars have already been born in this gas. And the most energetic stars are born first, the most massive energetic stars, well known in this process. And that energy is being absorbed by the hydrogen atoms and being re-emitted. And the re-emission simply happens in the red region of the spectrum, for physicists in the H-alpha line. So that gas is red because it's absorbing energy from the newborn stars and re-emitting it to the universe. Whereas here, the gas is blue because that gas is too distant from the star birth region, and so there's not enough energy to be reabsorbed and re-emitted. It's reflecting the light. So it's blue for the same reason the sky is blue. Sky is scattering sunlight. This gas is scattering starlight. So we already know scientifically, by analyzing scientifically a gas like this, that we have discovered a place where stars are being born. Let's jump rapidly ahead and come back, but everything I've said so far is happening in a galaxy, in our galaxy in that case. This is a galaxy. They're 10 to the 11th, or one with 11 zeros behind it, galaxies in the universe. We haven't counted them all, but statistically we can estimate that. So this is one of those many, many galaxies. What is a galaxy? It's a collection of stars, a family of stars held together by a common source of gravity that contains of the order of 100 billion stars. So that's one with 10, 11 zeros behind it, stars, like the sun. And it measures 100,000 light years across. Now let's pause for a moment. What did I just say? 100,000 light years. So if you have a friend that lights a match here, and you stand here, you have to wait 100,000 years to see that match. If you'd care to have a conversation with your mother-in-law, that's the best way to do it. It'd take 200,000 years to say, "Hi, Mom, how are you?" and get an answer back, "Not so good today," okay? I obviously don't have a mother-in-law, so I don't know what that experience is really like. Our galaxy happens to be very similar to this galaxy. However, you'll have to appreciate, as I flip to the next slide, that this galaxy and this galaxy are very similar. A galaxy is a very flattened system. It's like a tabletop. It's 200 times or more long than it is thick. It has a bulge, but it's very flattened. So if we look along the equatorial plane, so to speak, profile, we see it like this. If we look from the North Pole down, that is, we turn the galaxy around by 90 degrees, we see this. Now, we can't go out there and turn galaxies around, but galaxies face us in all kinds of directions. So we can reconstitute the fact that galaxies have these forms, okay, by seeing many, many galaxies. This is a spiral galaxy like the previous one. It, again, measures 100,000 light years across and has, 10 to the 11th masses of the sun. If this were our galaxy, and our galaxy is very similar to it, the sun would be here at the edge of one of these outer spiral arms. So forget the controversy as to whether the sun or the earth are the center of the universe, etc. We are in a galaxy that's one of 100 billion galaxies in the universe, and we're at the edge of our own galaxy as far as the sun goes. This is a mosaic reconstructing with a putting together of various photographs of the equatorial plane, the galactic plane of our galaxy, the Milky Way. It's done in infrared light so that we can penetrate to large distances in the galaxy because we are in the plane of the galaxy. So all the dust and gas is obscuring our view along the plane. It's like being out on a road here when there's a heavy fog. You cannot see very far ahead. But in infrared light, you can penetrate that and reconstruct the equatorial plane. And notice these incandescent regions like I showed you in the belt of Orion. Okay? These red areas, and what's going on here? What's going on, as I've already indicated, is that stars are being born. This is a piece of the previous slide in optical light, the light we see with our eyes. See these myriads of stars, but notice that you see these dark regions. What's it all about, Alfie? What's going on here? I mean, is that a lack of stars? And the answer to that question is rather easily come by over a long period of time. Another example of that. I'd like to show this, the North American Nebula. This is a cloud of gas and dust and myriads of stars in the universe in our galaxy, but here's the Gulf of California, peninsula of the Yucatan Peninsula. Florida is a bit fogged over, but that was even before the election count of 2 or 3 years ago. Chesapeake Bay, I think it's the greatest bay in the world, but you people that live on this lovely Seattle might differ. I was born in Baltimore, so California and Arizona weren't discovered yet. Well, let's get serious. Why this lack of stars here? Why are so many stars piled up here and there's a lack? It is just the opposite of a lack of stars. There's a veil of gas and dust that's hanging down here and obscuring the stars that are on the other side of this screen. I'm giving the camera guys some fits here, but that is, there are stars being born in this dark cloud of gas and dust. That's where the youngest stars are being born. The stars have already been born here. What is this about star birth? We've already discovered about 200 young stars at the edges of this dark cloud, embedded in these immense myriads of stars in the Milky Way. How do we know they're young stars? Straightforward. Take a spectrum of a star, analyze it carefully, and you know, in some cases, pretty exactly its age, in other cases, pretty approximately its age, just by the kind of spectrum that's there. And this is a very well-established field of studies. There's no doubt that we can, to a certain exactitude, tell the age of a star by analyzing its light through a prism, etc., and analyzing its spectra. So there's no doubt about being able to determine the ages of these objects. But here is a good example of how stars are born. This is an immense cloud of gas and dust that has begun to fragment due to its normal physics. It's an interplay of gravity and magnetic fields. It's been shocked by, say, a supernova explosion, which we'll talk about in a moment. At any rate, it's fragmenting, and any one of these fragments is going to begin to collapse according to the law of gravity. It's going to, by self-gravity, it's it's going to begin to collapse. Well, a gas that collapses, heats up. And a gas that expands cools down. But in this case, the collapsing gas is some several times the mass of the sun. So when it collapses, it raises the internal temperature to millions of degrees, and it turns on a thermonuclear furnace, a natural atomic bomb. That is, hydrogen is converted to helium, helium to lithium, to beryllium, to carbon, nitrogen, oxygen, to iron. And that's a star. A star is nothing but a cloud that's collapsed, turned on this thermonuclear furnace, and the energy from that thermonuclear furnace is being radiated to the universe. We have a star. In the next here, you see a very good example of the breakup of a cloud. In fact, here, we're going to get a cluster of stars. We'll have somewhere between 100, 200 stars born out of this single massive cloud of gas and dust, a family of stars. Notice again that the blue gas is here, the more red gas is here, for the same reason I mentioned at the beginning. This is a little bit of an aside, but just to introduce it, Hubble Space Telescope took a very clear view of a very small part of this galaxy that is very distant in the universe. It's about 4 billion light years out in the universe. And it found that stars are being formed here at a rate some 10 to 100 times the rate at which stars are being formed in our galaxy today. In other words, there were early epochs in the universe when stars were formed much more rapidly than they're formed in the universe today. I'm introducing you to the fact that the universe is evolving. Earlier epochs were different than the universe is today due to its expansion and many other factors. Here's another Hubble Space Telescope of a starburst region, we call it, of a galaxy, a starburst region where there's a burst of star formation. That's obviously very essential to astronomers to study the stellar population of the universe. We have to know the change in the rate of formation of stars with the evolution of the universe in order to study the evolution of the universe. What is this? Or this? They're dying stars, if you wish, dead stars. I'm treading on Bruce Ballack territory because he's a specialist in these objects, but nonetheless, I think I don't sin by saying they're dying stars where the star at the center here, in these cases, is typically a white dwarf, but in other cases, it can be a neutron star or even a black hole. That is a super dense bunch of matter that's dead, that can no longer, it has no longer any fuel to generate its thermonuclear furnace. So at the end, having burned up most of its hydrogen, helium, etc., it can no longer sustain a thermonuclear furnace, and it collapses for a final time, and it blows off the outer atmosphere of gas to the universe. Some stars die in a much more agonizing way. Here's a little star there at the end of the arrow. That's that star dying. Rather violent way to go about dying. And there's the result of that explosion. This star, in a matter of hours, 4 to 5 hours, increased its brightness by hundreds of thousands of times, let's say 200,000 times. Can you imagine a star in 5 hours getting 200,000 times brighter, that is putting out 200,000 times more energy than it did previously? That is a supernova explosion. There is the result of a supernova explosion. This is very different than the other dying stars I showed you at the beginning. It's a very agonizing death. It's not that peaceful sort of smoke ring out to the universe. Here is the famous Crab Nebula. There's a neutron star pulsar at the center of this. This is a star that exploded. not in our lifetime, but a few years ago, in the year 1054, so it was actually recorded by the Chinese. This star that brightens that much is easily seen by anybody who is used to looking up at the heavens. This is what this will be. That is, that explosion, this gas will disperse into the universe. This, after about 200 million years, it'll be dispersed in the universe like this. Now, I have not been around 200 million years to see this process. I may look like it. But we can reconstruct this process by looking at different objects at different distances in the universe. What have I just said? Light travels at a finite velocity. So I don't see the young folks in the front row here as they are, but as they were a millisecond ago. So Marcia, you're a little bit younger. The people in back as they were a millisecond ago. The sun as it was 8 minutes ago. Takes that long for light to travel. So when we see the sun set, it's already set 8 minutes before we see it set. And the center of our galaxy, as it was 30,000 years ago, the nearest galaxy to our own galaxy, the Milky Way, as it was 2 million years ago, and the most distant galaxies that Hubble Space Telescope has seen, as they were of the order of 10 to 12 billion years ago. So as we look further out in the universe, we're looking further back in time. And that's why I say we can attempt to reconstruct the evolution of the universe by looking systematically at more distant and more distant objects. We're seeing the earlier epochs of the universe in evolution. From this material left over from the explosion of a star, another generation of stars are going to be born. The material's out there, it's going to collapse, heat up, create a thermonuclear furnace. So we're going to have, from a first generation of stars, we're going to have a second generation of stars. But notice with each generation of stars, the material out of which the stars are going to be born is getting heavier, in the sense that the chemistry, the abundance, the chemical abundance is being shifted from very light elements like hydrogen and helium to very heavy elements like carbon, oxygen, nitrogen, and iron. Okay? It's just the way it happens. So the sun is a third generation star. And if it were not, why am I spending so much time on the birth and death of stars? Because if this were not happening, you and I would not be here. And that's a scientific fact. It's not sort of a romance, poetry, scripture, preaching. It's a scientific fact that the sun is a third generation star. And if it were not, you and I would not be here. That is, to make the chemical abundance, to make amoebas and toenails and earlobes, we needed 3 generations of stars to develop enough carbon, enough nitrogen, okay, to make even the most primitive living organisms. So that's why the birth and death of stars is so very important. Well, around at least one star, and we now have pretty solid evidence that this may have happened around many, many stars in the universe. After the star was born, so the star is at the center here, an artist's depiction of what happens, the material that's left over from the collapse, not all the material collapses in, material that's left over, by the laws of physics, have to form into a disk. To conserve angular momentum is the physical process. So the material that's all dispersed like this has to collapse into a disk, and when it does, it's much denser, so there are collisions among this material. You begin to form aggregates, and by the so-called snowball effect, you know, you roll a little snowball downhill, and by the end you have a big enough snowball to make the head of a snowman, etc. By this accumulation of material, you finally begin to form planetesimals and finally planets. Now, it's not that we know everything about this process, but as scientists, we know enough to know that it did not happen by a miracle, that it happened by ordinary physical processes, that a planetary system came to be. These are the collisions that caused that, and so a planetary system came out after the sun was born. And in that planetary system, this little grain of sand came to be. I say a grain of sand because you must understand by what I've said so far that it's a little grain of sand in the universe. It's one planet around one star, the sun, in a universe that has 10 to the 22nd stars, 10 to the 11th galaxies, each with 10 to the 11th stars. And there it is. On this planet, however, and perhaps on other planets, it's a big perhaps, an amazing thing happened. On this planet, we developed the capability of putting the universe in our heads. That is, I can stand here this evening and tell you our galaxy measures 100,000 light years across, and it has a mass that's equivalent to 100 billion suns. How can I say that? I mean, I can't go out there and do a marathon run around the galaxy and measure its circumference. I can't put it on a scale and measure how much it weighs. But I can apply to that galaxy the same law of gravity that I apply when I put myself on the bathroom scale. When I put myself on the bathroom scale, I measure the force of gravity of the Earth pulling on me. And when I measure the rotation of a galaxy, I'm measuring the force of gravity of the material in the galaxy upon every piece of material in the galaxy. I'm applying Newton's law of gravity, and Newton's law of gravity is determined by the masses of the respective objects. So I can actually measure with the same degree of accuracy the size and mass of this galaxy as I can measure my mass and size. You know, I weigh, at least before dinner, 176 pounds, and I'm 5'11" and a half inches tall. I can do with the same exactness a measurement of this galaxy. That's what I mean by putting the universe in our heads. It's an amazing achievement. We don't back up and think about it enough. I mean, the universe is no longer in kind of a blind evolution. In us, the universe is reflecting upon itself. And that's different than it just evolving. We're thinking about that evolving. And to some extent, though I'm not going to get into this, we have a responsibility. Once you can think about something and reflect upon it, you develop a responsibility with respect to that process. That's the whole process of ecology and all of that, which is not my point of discussion tonight. My point is the following. Once we develop this capability, we human beings are made such that, and scientists very much so in this way, that once we develop this capability, we find out that every time we acquire more knowledge, we're more ignorant. It's an educated ignorance. The questions are more pointed. They're questions that are more incisive. But it's honestly true. The more we know, in some sense, the less we know. More questions come to us than we can answer. There are many questions that derive from this ability to put the universe in our heads. I would like to just share with you very briefly two. Are there other planets like the Earth elsewhere in the universe? Now, I did not say, is there life elsewhere in the universe? Much less intelligent life. Further down south, east, we're looking for intelligent life on the Earth still. But sorry. I promised myself I would not get into politics. But that was a political statement. No, forget it. I did not ask, is there life elsewhere in the universe? Because if you ask that question of a scientist, you will receive a very cold stare and dead silence, because there's nothing to be said. There is no evidence for or against. So the question is really, to be precise, are there the physical conditions for life as we know it elsewhere in the universe? That is there a planet Earth around a star like the Sun, that it's at the right distance, so it has the right temperature regime, has an atmosphere, all those kinds of things, okay? If you ask that question, there's something we can stutter a bit today about a scientific answer. The other question is, where did galaxies come from? Let's address the first question. We have begun to make observations such that we have discovered 117. I didn't bring up the web page today, Bruce, but the last time I looked, we had discovered 117 planets about stars outside our solar system. Okay? Discovered. They're planets, absolutely discovered. We have not discovered a planet like the Earth because our technical capabilities have not gotten that exact yet, but we're on the way. We're on the way, there's no doubt about it. We need much higher resolution in our ability to detect these planets. We can only detect massive planets like Jupiter, typically, around stars where they're near the mother star, so to speak. But we've also detected planetary systems where there's more than one planet around a given star. So that's the beginning. Furthermore, we have detected, as is shown here, disks. This does not look like a disk to you, but it's because of the way in which we're viewing it. But this is a bunch of gas that is beginning to form into a disk about this star in the same way that we think happened in our planetary system. This is a whole series of stars. That one you can clearly see the disk. These are disks in formation, all of these photos taken by Hubble Space Telescope. And here's a magnificent display. Doesn't look near as pretty as this, but these are two disks in which a star is embedded in each. You can see part of the star here. Not only do we see the star in the disk, but in this case, we have identified the first planets born nearest to the mother star, which is precisely what we think happened in our solar system. What do I mean by we think happened? We typically take the solar system as we observe it today, and with all that evidence, why is Jupiter so massive? Why are all the planets that are way out there gaseous planets, and the planets that are near the sun rocky planets, so to speak? We know all that. We tried to say, what happened to make this planetary system? And what happened is that the planets nearest the sun were first formed, and then the giant gaseous planets were formed later. And that's precisely what we're seeing happen, we think, from our first evidence in this system here. What I'm saying is the first very, very primitive evidence, that's why we're stuttering, but the stuttering is in the right direction. We're getting more and more evidence that the existence of planets and planetary systems is probably very frequent in the universe about stars like the sun. Not every star like the sun, but statistically it must be very large, especially when you have 10 to the 22nd suns. Well, you have 10 to the 22nd stars. About 30% of them would be like the sun. The answer to the question, we're beginning to probe by observations as to whether there are the physical conditions for life elsewhere in the universe. Furthermore, you could talk statistically, but statistics can be very easily, lead to lies, right? We all know that. But nonetheless, if you look statistically at the universe, this immense number of stars, and the sun being a normal star, statistics overwhelmingly tell you that there must be planetary systems elsewhere in the universe. That is, the physical conditions for life. Galaxies, there's a beautiful galaxy again. Where did it come from? We don't know. When I say we don't know, I mean we don't know. There are all kinds of ideas, and we're getting increasing evidence for this. But I'm trying to impress you with the fact that we don't know it all, we scientists. Now, not knowing it all in this case is pretty fundamental, because galaxies are the building blocks of the universe. It's galaxies that we measure to establish the expansion of the universe. It's galaxies that we measure to study the distribution of matter in the universe. And yet we don't know where they came from. I mean, imagine yourself, you're building your dream home. Saved up enough money, put it in the bank. You get an architect, you work hard with the architect, you know. Curse him out at times, but finally you get the right plan. You hire a general construction person, and they're about to start building your house, and a friend comes and says, by the way, you know that general construction company you hired? They don't know what a brick is? Well, you'd be a little hesitant to go ahead building this house, especially if it were going to be built of bricks, if the guy didn't know what a brick was. And in a sense, that's where we are with our kind of knowledge of the universe, the essential building blocks of the universe. We don't really know where they came from. On this one picture here, there are the order of 100 galaxies, all of which form a family of galaxies. They're all related to one another, like the planets are related to the sun. They have a common center of gravity. On this slide, there are some 2,000 galaxies, all of which belong to the same family of galaxies. This is a picture of a big piece of the universe. It's not a picture. Each point here is a galaxy. This is a study. There are much more sophisticated studies now, but this gives an example done some years ago at Harvard of how are galaxies distributed in the universe. Well, this sort of slice of the universe measures across 200,000 times the diameter of our galaxy. So imagine, you could take our Milky Way and put 200,000 of them across here. So it's a big sample of the universe. And what it tells us is that galaxies are not distributed uniformly. There's the Great Wall, not the Great Wall of China, but the Great Wall of the universe. Either that or Orion come back to haunt us. They're big empty spaces here. You have to think in 3 dimensions here. This is a big empty balloon. Why? Why the distribution of material in the universe on a modestly large scale? We honestly don't know. We're beginning to get some inkling of the birth of galaxies. Hubble Space Telescope detected these objects back about 12 billion light years. By the way, the best age we have today of the universe is 13.7 plus or minus 0.2 billion years old. So these objects are only about 1 to 1.5 billion years after the beginning of the universe. So we're looking way back at the early epochs. And it appears that these globs are aggregating. They're getting together, embracing one another, if you want, until we think these most distant galaxies we've ever observed with Space Hubble came out of this. So from here, we got to here, but there's a big bridge in between that we really don't understand. So though we have some clues, we don't have a thorough understanding. That's an example of the degree of ignorance and the exciting questions that come out of the fact that we can put the universe in our heads. Now what I would like to do is to, since I put on this Halloween costume, is to play the religious believer before you. Say, are there any religious implications? Is there any way in which science can talk to religion and not come out just with a lot of mooing, but with something that, is worth thinking about? In order to do that, I would like to take a moment to tell you a story, and that's the story of Sherlock Holmes and Dr. Watson. Many of you may have read the series of detective novels of these British detectives who lead very sedentary lives. I mean, they go to the scene of a crime. Dr. Watson is the philosopher type. He has all these great ideas about what motivated this crime and all. Sherlock Holmes is the empirical one, goes out and gets all the data and finds the clue that leads to a solution of the crime. But these two guys are very sedentary lives. They go out, they come back to the laboratory, they sit there and have their morning tea, their early afternoon gin fizz, their martinis later in the evening, and they try and solve these crimes. They get this strange idea with their sedentary life of going on a camping trip, just an inspiration, you know. So indeed, they follow up on it. They buy all the best equipment, you know, good sleeping bags, air mattresses, camping stoves, nice big tents, you know, because they're, in addition to being detectives and sedentary, they're rather corpulent, I should be talking, but, you know, so they need a big tent. Even though there are two of them, they get a four-man tent. They go out camping. They try and find a mountain in England, but there are none, so they settle for a hill. And they go set up their tent, nice campfire, have a good meal, wine and steaks and all that, and go to bed. But they've never slept on the ground, even with this nice tent. So one wakes up, the other rolling around. They both wake up together. And Holmes says to Watson, "Watson, what do you think about that?" And Watson says, "Well, that is magnificent." He said, "They tell me that that's the plane of our Milky Way going across there. That's if you're speaking astronomically, Holmes. If you're speaking theologically, they tell me that there are billions and billions and billions of galaxies, so there must be a God. There has to be a God if the universe is. But if you're speaking meteorologically, Holmes, I mean, we're going to have a beautiful day tomorrow for hiking and all because the sky is so bright and all of this. What do you think, Holmes?" And Holmes says, "Watson, I think somebody's stolen our tent." Now, I tell that for a purpose. I would like to steal your tent and my tent. We all have a tent, right? From what I've told you, we all have our sort of way of viewing this. If we're religious believers or not, we've already drawn certain conclusions. To the best that we can, let's just look at it, get some idea of if someone is a religious believer, what does this universe that, to the best of my knowledge, is a good description of what scientists see and observe and try and reconstruct by their modeling of how the universe came to be the way it is today, the expanding, evolving universe. And if we do that, let's very quickly, you know, sort of give this, by the way, is the sky that Watson and Holmes saw when their tent was stolen. This is the sky over Mount Graham, Arizona. It's one of the best observing sites in the world. That is the plane of our Milky Way, and there's Phoenix and Tucson. As the universe grew older from time 0 to this should be 13.7, as I said, but that makes no difference to our discussion. As the universe grew older, distances got bigger. Okay, distances increased. And this is curved because as the universe expanded, it was also being braked in its expansion because there's material in the universe, came to be in the universe, and material exerts gravity wherever you have mass, and so it slows down this expansion. It pulls on the expansion of the universe, so to speak. So it's not linear, it's slowing down. That does not mean the universe will ever stop in its expansion. And in fact, we have fairly solid evidence that it's not only not going to stop, but it's accelerating, which creates all kinds of problems for the law of gravity. How could this be that there's overcoming the gravity of the mass in the universe to accelerate? But that's a separate story. In this expanding universe, these things happened. Now, because we scientists put an arrowhead on here, does not mean that we know the exact time at which this happened or even the order in which it happened. Where some stars formed first and then galaxies later, there is a bit of confusion here. But nonetheless, the general picture is the solar system did form. about 4.5 billion years ago, maybe a little more. First microscopic life forms came to be at about 12 billion years after the Big Bang, maybe 11.8 or so. Why did it take 12 billion years to form an amoeba? Well, we've already said something about that. There are other reasons. We needed the chemical abundance, and we couldn't have that until we had 3 generations of stars. And generations of stars, like human families, overlap. We have grandparents and parents and grandchildren at times living in the same house or the same community. The same with star generations. They overlap. So 12 billion is about the right time to have 3 generations of stars. So we needed that before we could have life forms. Now my question is, I'm jumping off not only as a scientist, but as a religious person, and that I'm outside my field when I talk about this, but that very seldom slows down a scientist, is what happened between here and here when you and I came to be. Well, to get some idea of what happened, let's look at this. All this is the most simple measurement you can make as a scientist about things. Measure how much they weigh, so to speak, the mass of an object, and measure its size. So measure yourself and put yourself on here. You are so many meters high and you weigh so many kilograms, put it on here. We put on there the proton all the way up to the visible universe. And it's amazing that everything more or less fits. By the way, for any mathematicians or scientists in the crowd, the log-log is not corrupting this relationship, obviously. I mean, the fact that there are no objects here and no objects here is not due to the log-log plot, obviously. The log-log is necessary because we're going to, from the smallest to the largest objects in the universe, and to get them on one picture, we have to do that. But nonetheless, the important point is, nice relationship. All living beings fit this relationship, including ourselves. So while this is not a proof, I don't propose it as a proof, it's a strong indication that we came out of the universe in its evolution like everything else did. The universe in its evolution created ever more complex beings, okay? And we fit into that evolving picture of the universe. This is another indication of it, a little more complicated. All it plots is the ability to store data, memory, against the ability to compare 2 pieces of data to one another, like we did in the previous slide. And you see we're there. We're not at the top, by the way, they tell me, okay? And a smart missile is over here because it doesn't have to be any smarter. You don't have to, all it has to do is find that guy and shoot him, you know? The British Library, it's true of all libraries, but my closest friends are British, so I accuse them of being the most stupid of the libraries. I mean, a library is dumb. It can store a lot of data, but it can't do anything with it. I mean, one book, best of my knowledge, cannot talk to another book. So if you put all the data from a given telephone directory in a computer, a book, and then you put all the data from how bright is the sky over Seattle, there will be a correlation. The more telephones you have means the more people you have, and the brighter the sky over the city is. So you could, 2 books cannot talk to one another except through a computer. The point is here, there's in general a relationship, even with this slightly more complicated relation, and that says something about, we're part of the universe in evolution. How did we come out of it? Now, I'm really treading on foreign territory, but I think I would take a very strong position. I think it would be scientifically stupid not to accept some process like this in the coming to be of the human brain. I am not defending evolution from one species to another. I'm leaving that open, okay? But that there was a process of what can be called chemical complexification, the building up of more sophisticated chemical organisms until we got to the human brain. There's little doubt that that is the true process in which the human brain came to be. There are big lacunae in this process, But various fields, paleontology, chemistry, physical evolution of the universe, and cosmology, etc., all support independently this kind of process. We're going to have an exam on this tomorrow morning, so I mean, I'm not enough of a chemist to understand all this goings on, but just look at it. H, C, N, and O continuously repeat themselves, hydrogen, carbon, oxygen, nitrogen, in ever more complicated molecular configurations until you get to the amino acids, the sugars, etc., the essential building blocks of life. And I propose that this chemical complexification in an expanding, evolving universe is essential to understanding our place in the universe. Now let's pose the big question, which obviously has many religious implications. Did this happen? If what I've said thus far this evening has any semblance of the truth scientifically, did this happen by chance or by necessity? That's the classical question, of course, in this, and that obviously has implications. If it were by chance, who needs God? It just happened. That's the way the universe is. It just happened. But if it happened by necessity, that it was determined to happen, then one would be led to think of somebody made it happen. Somebody designed the universe so that it would happen. Those answers are both wrong to me because the question is wrong. Because the question, first of all, is not complete. There's a third element in this discussion. It's not just necessity or chance. It's both necessity and chance, but with a third element that I call, for want of a better word, opportunity. That is a universe that is fertile, that offers so many opportunities, 13.7 billion years old with all these stars and galaxies, all this complex chemistry going on as time goes by, that it was, I'm going to use the word, inevitable that the human brain come to be. That is, let me say what I mean by a chance process, because it's a statistical consideration. Will this hydrogen atom in the early universe become a complex molecule, a part of a complex molecule? Well, two hydrogen atoms meet. And by the laws of nature, necessarily, they're going to form a hydrogen molecule, H2. That's the way the universe works. But when they meet, the temperature and pressure conditions are not such that they cannot make a hydrogen molecule. So they wander around the universe, and there are trillions and trillions of atoms wandering around the universe, and they continue to meet. Well, who's to be surprised if in a universe so old, relatively speaking, with so many opportunities, that once in a while, 100, 1 billion, 1 trillion times, you form a hydrogen molecule. If you form that, then the hydrogen molecule, if it meets an oxygen, is going to make water, necessarily, if the conditions and circumstances are correct. And so on, in a relatively very old universe. So many opportunities offered for this so-called chemical complexification until finally you come to the human brain. If it is something like this, then, let me say this. Einstein, it is said of him, and it's true, I mean, he's written as much, that God, said Einstein, does not play with dice. He referred directly to quantum mechanics, but it's a more general statement about his view of the scientific process in the universe. That God, whatever God was to Einstein, determined that the universe would evolve in a certain way. He determined it. To give an example, the biomolecular Nobel Prize, Christian de Duve from Belgium, in a fictitious conversation with Einstein, says, "Albert, you're very bright, it's obvious, But God did play with dice because he loaded the dice. And what he means by that is that God, if I believe that God made the universe, then he made a universe that is so fertile with the opportunities for life that he did not necessitate that it happened. He provided the opportunities that it would happen. And that's a very different point of view than necessitating it would happen. It's such a point of view, and I embrace it for what it's worth. If this is a strange tree, a tree of the universe, everything that ever happened, I have to put this universe rooted, but I'm not going to talk about how it began, this universe. That's a whole other story. From its beginning, having roots, it sprouted. And this tree of the universe preserves everything that ever happened. The first quarks, first protons, first galaxies, birth of my grandmother, my toenail. Everything that ever happened in the universe is here. No dead leaves fell off. Nobody came along and sawed off dead branches, etc. It's all there, but blow a little breeze through this tree of the universe, and what do you see? You inevitably is the word that I use, but invent your own word. I will not use the word necessarily. I will go as far as inevitably going to see something like this. And that is because the necessary processes are driving this evolution, but the chance processes are also involved, so this could be slightly different. I mean, we could have, arms coming off a belly button in our back. It would look strange, but it wouldn't look strange if all of us were wearing our arms that way. There could have been in this chance process certain different kind of evolution of the human being. I kind of insist, living long enough in Italy, that if we develop the power of speech, you would have to develop arms. Because an Italian cannot speak without arms. But sorry to those Italians and of Italian descent, but it's true. Why is the human being at the top? Because we don't know what else to put at the top. If you find a more complicated machine, I'm speaking as a materialist now, for purposes of this talk, you put that machine at the top. The human being is, and we're still evolving, of course. Well, if anything that I've said is true, then let me end by a little preaching again. If I believe in God, okay, and I do, that's a big if. I don't impose that upon anyone, because religious belief is a very personal affair, etc. I have not come to believe, because of anything I know about the universe, I have not come to believe through any purely rational process. I look upon faith as a gift of God, the gift of God himself to me, that I fortunately received. It wasn't a miracle. Growing up in a certain family, certain education, you question, etc. You go on. What I'm saying is that faith to me is not something we merit, not something we reason to, it's something given. It has rational foundations. I don't think I'm stupid to believe. You may, but I don't. I'm convinced that they're rational foundations. But that's not adequate. My faith trend goes beyond reason. It's irrational to me. It's not irrational. But let me get back to the if. If I believe in God. Does this universe that I've described say anything to me about the God whom I believe made this universe, whatever that means, make this universe? But I see the universe as dependent upon God, a maker. My knowledge of the universe, does it say anything to me about this? God, it sure does. It says that God is not a dictator. God is not he didn't make a universe like, construction of a clock where all you do is wind it up once in a while and it keeps running. That he made a universe that has a dynamism of its, a creativity of its own. Let's ask the hard question. If the God I believe in were in the universe, I believe that God transcends also outside space and time, but for purposes of argument, let's exclusively put God in the universe at about 2 billion years after the Big Bang in this evolving universe. Would God know that human life was going to come to be? And my honest answer is no. It would conflict with my scientific knowledge to say that he or she did, because God cannot know what's not knowable. And it wasn't knowable. The universe has such a dynamism to it, as I've tried to describe it, necessary, chance and opportunity together, that I see God as one who hoped, caressed the universe, if you want, that human life would come to be, but did not necessitate that it would come to be. That's a different God than I was taught about when I went to school as a young kid. It's a challenge to the faith. I don't think it's... What it is to rethink religious doctrine in terms of what we know as scientists. Rethink it. Subject it to further rethinking, If you can do that and sort of your faith is firm enough to do it, I think it's a very enriching experience. But I'll stop preaching now, and thank you for listening to me, and welcome any sort of questions, debate, ideas of your own that you'd like to offer. Thank you, Bruce.
I guess I still don't understand why you believe there's a God, and could you explain that?
If I could ultimately explain it, then it would not be God, because God is beyond explanation. So if I could ultimately explain my faith in God, I'd be explaining something other than God. So I have to say that. It's my personal experience, and there's a long tradition, long religious tradition. St. Thomas Aquinas, at the end of this voluminous work on trying to understand God in terms of the universe as he understood it in those days, an Aristotelian universe, etc., said it's all straw. I have friends who say, George, every time you mention the word God, he's further away. And there's a real truth to that. Okay, that's the background to trying to answer your question. God is not explanation. God is love to me. And as a loving being, God gave himself in love to me. Now, how am I going to explain that? I mean, how are you going, even at the level of human experience, would you please explain to me why you married the woman you married? Because she has blonde hair, blue eyes, is so tall? I mean, all of those things entered in, but there's that ineffable, that unspeakable, that we cannot explain a lot of human experience. And if that's true, and I think it is, then how am I going to explain this experience of a love relationship with God? So it defies explanation. I still hold that it has a rational groundwork to it. I am not embarrassed ever by saying that I believe in God, that you're stupid to believe in God. It doesn't make any sense to believe in God. That's not correct. And if we had more time, I'd stand up and have a strong drink first and
This program was sponsored by the Jesse and John Dans Fund. Since 1962, these lectures have been a forum for distinguished scholars of national and international reputation who have concerned themselves with the impact of science and philosophy on man's perception of a rational universe.